Okay, let's continue. Well, the contents that we will follow today, just a really short introduction and motivation from the copper pyrometallurgical refining. We will move then to a quite complete thermochemical study of this copper anode furnace, and we'll end up with some conclusions. Okay, first of all, really quick, this is the copper refining path, both in pyrometallurgical and hydrometallurgical, and we are focusing here in the fire refining. We have an input, which is 99% molten copper. We want to remove the two main impurities here, which are sulfur and oxygen, and have solid anodes with 99.5% purity. Okay, so for that, first, we are desulfurizing it using hydrogen, blowing it, and we want to reduce sulfur as SO2, but we will also increase the amount of oxygen. After that, we want to remove that oxygen. We usually use natural gas or methane. I will use them, both of them. And we can also reduce a little bit of sulfur, but mainly we want to remove the oxygen in solution. And we will remove oxygen as CO2 and water vapor. Okay, so our motivation here to change this methane to hydrogen is that the climate impact of copper is 3 times higher than iron per kilogram refined. And this process is around 18% of those emissions. And the efficiency is quite low. It's only about 30%. So we want to change both of things. We want to remove the emissions of the process, and we want to increase the efficiency. And we think that hydrogen could be a way. We are using ChemApp for Python, as I said, but the approach is quite complicated since we saw all the bubbling coming. That's quite far away from chemical equilibrium. So we will we have used ChemApp for Python and quite a lot of calculations to try to define this process as the way we have done. So we have divided this furnace into these 4 steps: desulfurization, deoxidation, casting, and solid anode. And we will work in 2 different ways. We will divide it into the liquid state to the right and back and the solid part in which we already are casting and have a solid anode. We will study all the things that we will run through all of them now. Okay, so let's move first into the solid part and see the minor impurities that we have and how they are affecting these anodes. Well, this is a chemical analysis that we obtained kindly by our colleagues from Atlantic Copper in Spain. These samples were already desulfurized, but not deoxidized yet. So we can see that we have quite a bunch of elements, but how do they affect and how are they, if we see the microstructure that they generate? We have here we performed some SEM images, and the phases that we saw, the phases that we saw were pretty nicely predicted by our database that we use, that is FSCOP. We see a matrix of pure copper and 3 types of oxides. It's just the darker ones are copper oxide, and the other 2 are complex oxides, which I'm not reading because they are quite difficult to pronounce. Let's move to the next part because we have we have some impurities, but these impurities could somehow affect the deoxidation, which is the important part here. So we started again with ChemApp for Python. We use this composition that we see back to the left, 1% oxygen, and individually we increased the amount of each of the impurities and divided them by the ones that increase the oxygen activity and thus will make it more reactive, and the ones that decrease the oxygen activity. And we see that we have some of them in which that we expect to increase in the following years with more recycling copper that comes mainly from electrical components. And that's something that could somehow hinder this deoxidation from the thermochemical perspective. And now let's move to the liquid part of the furnace, because the 2 main impurities are sulfur and oxygen. and maybe they can affect each other somehow. From now on, we will a little bit forget about the minor impurities and focus on these two impurities. So this is just a solubility diagram that we prepared regarding the weight percent of oxygen and sulfur. And well, as we can see, this type of diagram can be used somehow during desulfurization, since we start with quite high amounts of sulfur or lighter at the beginning than at the end, and we increase the amount of oxygen by bubbling it. And that's why we move to this part where SO2 is stable and then we released, but we will also increase the amount of oxygen. And we see that there's a thermochemical limit of removing sulfur with oxygen. But we can also, during the same calculation, see what happens to each other elements, the activity of the other elements. So we can plot also using ChemApp for Python, both weight percents of both sulfur and oxygen, and see the activity of oxygen to the right and the activity of sulfur to the left. Take a look that this is 6 times smaller than the sulfur activity. And that's something that also helped us during the desulfurization process, since as we reduce the amount of sulfur, we are also increasing the amount of oxygen, and that will also make it somehow easier to deoxidize after this desulfurization. So let's move to another property, which is the density of copper. The density of copper is quite, it can be quite important, both for industry, for simulations, for CFD. So here we have comparison. The 2 dotted lines are 2 different literature reports that we found. And the continuous line is the one that we obtained of pure copper at different temperatures. And well, this is just a usual fit that we use. And the dotted line up is obtained from quite a lot of experimental results. So we see that we're quite close in our calculations. But we can go a little bit farther, because in this process, we don't have pure copper. We have pure copper, and we also have oxygen. So we can also perform and check what happens to the density, in this case at 1200 degrees, which is quite a common temperature in this furnace. And we see that we obtain different values, but well, I think that the model that uses FactSage for this database is the Birch-Monaghan equation of state, and the other one uses an ideal mixing. So that's something nice that we didn't find any literature, but we trust with the other results. But we can even go farther, because we also said that we have sulfur in the system. So how can we also see what happens with the density with sulfur and oxygen? So we have here a plot of densities at 2 different temperatures, 1150 degrees and 1400 degrees. And we can already see here some trends that happens when we increase the temperature. We are reducing somehow the density, and that's also something that happens with the amount of sulfur and the amount of oxygen. But this is somehow a graphical view, and we cannot maybe see it that much. So what we did next was performing a quite nice amount of calculations, over 600,000, in those ranges that you see here, from 150 to 1500, and in temperature, oxygen up to 1.6 and sulfur up to 0.6. And just with all those calculations, we did a quite simple polynomial fit. And now we can see a little bit better how each of them is affecting. That's more graphical, maybe, that we can see it easier and calculate maybe a little bit easier the density, even with and the error is also quite nice, with a mean absolute error, which is below 15 grams per cubic decimeter. But now let's move to the hydrogen part. This type of furnaces have oxy-fuel burners that we want to maintain the temperature, but also we want to keep the atmosphere reductant. So we wanted also to simulate that using thermochemical tools. And here we have the way we did it was setting adiabatic reactions between oxygen and each of 2 fuels. And then the way we plotted the data was setting first the molar fraction of the oxidizing species of the outputs of the equilibria, and the reductant, sorry, first, and the deoxidation then. And then for each of the calculations that we have to think about, we have to think about them in a vertical line. We performed a new equilibrium with the blister copper that we said, 1% oxygen, and check how the oxygen activity is changing. That will also give us a hint of how we expect the atmosphere to be reductant or not. And we see that the maximum temperature that is reached by an adiabatic flame of hydrogen is a little bit higher than for the case of methane. We have a higher fraction of reductant species for methane, but we see that on industrial levels, are usually in this range, and about 2 or 3 molar ratio, they are not that different. And the reduction performance, we see that it's quite similar if we consider it as the change of activity in oxygen at 1200 degrees. So now we can move to maybe the key point, which is as reductant as this bubbling. How can we change that? So first, we performed a really simple equilibria, which is hi. I'm losing myself. We set an equilibria of 100 grams of blister copper, 0.99% oxygen, 0.01 sulfur. And we set an equilibria with increasing grams of reductant. And as we can see here, I said that we removed a little bit of sulfur, but as it's a closed equilibria, it comes back as we lose oxygen from the melt. But the most important part here is maybe the amount of oxygen. We see that an industrial level would be around 0.15% of oxygen, and we see that at that moment we need around 4 times less methane than hydrogen. So I guess that means that hydrogen is no longer valid, and I should find another job. Or we can see what happens, because in reality, we see that the efficiency of methane is only about 30%. And the first publications that are done with hydrogen see that the efficiency is higher. So how can we think about that in a thermochemical way? So this was quite a simple equilibrium at 1200 degrees. But is it that easy to decompose this methane? Because maybe it's not that straightforward. This is a really simple plot of 1 mole of methane, and we increase the temperature. And these are the graphite and the hydrogen are the ones that are reacting with oxygen to form CO and then CO2 and a water vapor in the case of hydrogen. This is a high endothermic reaction. And the energy in order to obtain this graphite and this hydrogen is obtained from blister copper. So somehow we are contributing to the reduction of the temperature of the melt. And well, it's each of the compounds, the ones that react. So in a new set of calculations, we said, okay, let's try to introduce this plot into the previous one. How can we do it? First of all, we set the equilibria that we said that we saw about CH4 at every single temperature from 0 degrees to 1200. And then the results that are coming from that equilibria, that are graphite and hydrogen, we set an equilibria with the blister copper that we saw. So at 0 degrees, we have no carbon and we have no hydrogen. So as we can see in the left, there's no reduction at all. In the case of hydrogen, it's not the same. It's independent on the temperature, what we observed. But in the case of methane, we see that we need to increase quite a lot the temperature of the gas itself in order to be able to reduce. And how much is that? How can we get a little bit deeper? Well, it works. We see that as we increase, it's just the same, but in a more visual way, we see that we are increasing the temperature of methane, and we are also increasing the reduction. So there's one point at which methane now becomes more reductant than hydrogen, but we need to reach that temperature in the case of methane. And that temperature, just to be a little bit more exact, is around 472 degrees. So now we change a little bit the way we think. That is, it's not that hydrogen has to be better than methane. Of course, it has to be. But are we able to increase the temperature of methane up to 472 degrees in order of it to be better than hydrogen? And well, that's the temperature that we have to reach. And of course, it's not that easy because the bubbling is quite violent and it's quite hard to obtain the temperature. We will depend a lot on flow type, heat transfer, and the residence time, which is not quite long. So that's something we have to take into account. Well, I think I'm a little bit out of time. So, well, these are just some conclusions of everything that we have exposed today regarding the impurities, the sulfur and oxygen activity, and then the density work that we have done. And finally, the direct comparison between methane and hydrogen. And that was all by my side. Thank you very much. Well, this and some more results that I don't have time to are coming on an oncoming publication in MMTV. And well, of course, we are open for discussion and for any comments that you have. Thank you very much.